If you recall, last time we were discussing about methods used to find out evapotranspiration information, measurement as well as estimation. And at the last we learned about factors influencing evapotranspiration. Do you recall that? That is part of crop water requirement. Can you see the slides?
Yes, sir.
Okay. So we were discussing previous to this different methods to find out information about ET. If we know ET, we can find out ETC, means from potential evapotranspiration or reference evapotranspiration, that is ET0. We can find out crop ET, and that is important to plan or to design irrigation in terms of requirements as well as time of irrigation to the crop. So these are the factors we discussed: meteorological factors, basically, then crop factor, type of crop, and management and environmental condition which are influencing the evapotranspiration. This is general idea to give you general. It is not very much precise because it varies from one particular climatic condition to another condition. Say for example here, rice, which is grown in every part of the country almost, starting say from arid region, some parts or some area in Rajasthan, Gujarat as well, rice is cultivated, and here in West Bengal, where maximum rainfall is there, rice is as well cultivated. So it's basically the range minimum, that is without any loss. So crop water requirement, that is the simple idea in terms of millimeter, depends on growing season or growing period. It is the amount. Just like sugarcane requires maximum amount of water, maybe 1.5 meter you can see to 2.5 meter, that is high variation to grow sugarcane. In that sense, this requirement of water is simply accumulation of daily ETC. We can say ETC, that is crop, from day 1 to day n when the crop is harvested. So if we know that irrigation requirement of the crop, say simply by accumulating ET, we can find out when to irrigate the crop. Simple idea, earlier as well I told you that we need to find out what is the soil moisture at which the yield is getting reduced or it is getting affected in a substantial manner. If you recall, I plot a graph like this when it is complete saturation, field capacity level, not saturation. Yield is suppose this maximum, we can say 1 is the maximum, yield will be maximum, and when it is reducing soil moisture content to a say permanent melting point or melting point somewhere here, yield is not a function of soil moisture as a linear, it is not a linear function of soil moisture, but it goes something like this. It will constant, then it will reduce slowly, and then it will decline very fast like this. So up to this somewhere, it is not this substantial loss of yield, or you can go somewhere here. So this particular condition theta, we need to know to avoid any loss in terms of crop return or crop produce. Either we can find out this amount by, if you recall, by measuring soil moisture content, earlier it was, or simply if we are counting the days, we can simply accumulate the amount of evapotranspiration to reach the soil moisture. Like at field capacity, suppose theta field capacity is moisture content, you can find out how much is the water per unit depth or for a specific depth D or Z in terms of root zone. So how we do this? This is basically bed wise or mass soil moisture content volumetric. We need to convert this. To convert this in volumetric, we are simply multiplying by afferent specific gravity, and to find out in terms of depth in a particular root zone D, we are multiplying this. So this is the depth of water at say particularly field capacity level. It's in fraction condition. If we multiply this apparent specific gravity, it will become theta volumetric moisture content, and Z is the root zone depth, to find out how much water in terms of depth is there. So we can find out this at particular time t as well. So D at t we can find out theta t into As into Z. That is simply depth of water that is remain. So difference between D to dt, that is the loss of water in these number of days. And that is simply function of evapotranspiration. So if we are accumulating daily or summing up daily evapotranspiration, the moment this amount of water is there, it is simply time to irrigate the crop to avoid any loss of return or basically produce or yield. So this is simple idea of irrigation planning. So two way we can go, either by measuring the soil moisture or accumulating the evapotranspiration in that particular area to find out the time when we should irrigate, or a specific time when critical or threshold soil moisture may be reached. So this is net irrigation requirement in terms of depth. Now this is the same. This is the field capacity, that is F, it is written moisture content at field capacity, that is weight basis, and this is moisture content before irrigation or at the time of irrigation or particular time t. So this is the difference between field capacity and present moisture content, or just before irrigation moisture content. It is in weight basis percentage, so divided by 100, and this is apparent specific gravity, and this is depth of root zone, depth of ith layer of the soil within the root zone. Now here I denotes, here initially we have taken as, suppose this is the depth, sorry, capital D it is written, depth of soil where roots are there, suppose here. Now question is, we are assuming that it's a layered soil, suppose 3 layer or 4 layer, whatever number of layers we can assume depending on the characteristics of soil depth wise. So these layers from I is equal to 1, the first layer at the top to n, that is the bottom maximum, it is covering the root zone depth, and this is the simple idea of finding out net irrigation requirement at the time of irrigation, how much water in terms of depth it is required. This is the same equation earlier we have learned, theta field capacity minus theta T at the time of irrigation into 100 if it is in a bed basis percentage moisture content into apparent specific gravity into Z, that is the depth of root zone, the single root zone depth we have assumed. Depth will be in same unit in which Z we have taken. So this is the net amount of irrigation. However, if we are applying, suppose say water from the source to the field, it is, you recall we have learned conveyance system. It goes through a conveyance system, and in this conveyance there are certain losses of water. If it is open channel, lateral losses, vertical losses, and if it is a pipeline, maybe some leakage. So we need to supply the water from the source in little more quantity to reach here in the field exactly the amount D, because there is loss in between supply line. So there is term coming grass irrigation requirement. This is net irrigation requirement. And if we need to find out how much water we need to pump from the source to the field under certain efficiency of conveyance condition. So it's coming into picture the grass irrigation requirement, that is net irrigation requirement divided by field efficiency of the system or conveyance efficiency of the system. So there are number of aspects of efficiency understanding, and we will be discussing at the last of this particular topic. So this is the idea how we are planning, how we are estimating the amount of irrigation water, either in terms of net exactly, or it is a grass irrigation requirement in the field. Two-way soil moisture accounting, or it is ET accounting. So now it is coming irrigation frequency. After how long we should apply the water in the field? It's a simple idea when it reaches to the threshold soil moisture content. That can be measured either by soil moisture measurement or by ET measurement. So irrigation frequency refers to the number of days between irrigations during period without rainfall. Also simple idea, after how many days we are irrigating. So this is dry days, we are not irrigating. Here we have applied water, here we have applied water. So after how many days it is irrigated. So refers to the number of days between irrigations. It depends on, simple idea is consumptive use rate of the crop. So to reach from here to here, or in terms of time, it is simple two-base system, ET. So depends on consumptive use, that is almost equal to the ET, rate of the crop, and amount of available moisture in the root zone, that is theta T basically we have taken here. Irrigation frequency is also the function of crop, soil and climate. Which crop, whether it's suppose sugarcane, it will take more water or uses more water in terms of evapotranspiration. So its frequency will be more. In less number of days, we need to apply water. If it is a sandy soil, it will be more loss of water from the area. So it is frequent irrigation requires. Climate, if it is a dry climate, say arid condition, automatically ET rate will be very high. So in that sense, frequent irrigations will be required there. So function of crop, soil and climate is this irrigation frequency. Sandy soil requires more frequent irrigation, that is soil type here, and moisture use rate varies with crop type and climate condition. Simple idea what we have discussed here. Crop type and climate also affect the moisture use rate, like ET. What is the rate of ET? Because you have seen ETC is equal to Kc into ET0 simply. So from reference, it is matter of crop, which particular crop. So moisture rate varies, or moisture use rate varies, that is basically ET with respect to crop and type of the climatic condition. If it is dry, it will be faster rate of use of water. Now, if we know that this is irrigation requirement, this is irrigation frequency, how to find out when to irrigate? So it's basically irrigation frequency. In designing irrigation system, suppose we are planning to have irrigation system, channels and water source planning, then design of irrigation system, it is the time in days between two irrigations in the period of highest consumptive use. Means, suppose for an example, you have crop period of say 100 days. You have seen Kc, it is varying from here minimum to increasing to constant and then to decrease. So where we should use this frequency? So period of highest consumptive use, this is the maximum water it is using here at fully mature. So ET is highest here. So design frequency means system should be designed, means our say pump, supply line or source of water should be designed in such a way that it can supply this maximum use of water conditions, support this. So design frequency is simply field capacity of the soil in effective crop root zone depth. Field capacity means suppose it is field capacity. So depth of water AS into root zone depth, that is D, minus moisture content of the same zone at the time of starting of irrigation, minus it is the same theta at the time T into AS into Z. So this is simple idea. We are getting how much water it is required in terms of depth and peak rate of soil moisture used by the crop, that is ETC, that is crop, and that is peak time. So we can find out in terms of, this is the depth term of water that is to be irrigated, and this is ET, that is the maximum. So we can find out less number of days relatively to this particular portion or this particular growth period of the crop or this growth period of the crop. So frequency means how frequent it is irrigated. It is the answer here. So irrigation frequency, once you know, it's only matter of finding out how much water it is depleted from the soil or effective root zone depth. So once you know the irrigation frequency, irrigation period we need to know. So what is irrigation period? Number of days that can be allowed for applying one irrigation to a given design area during the peak consumptive use period of the crop being irrigated. Irrigation period means how many number of days, again means after how many number of days the crop will again get irrigated. So number of days that can be allowed for applying one irrigation to a given designed area during the peak consumptive use period of the crop being irrigated. So suppose it's a big area, so it is within 1 day or within 2 days, it's like that. So we need to divide this area in such a way that it is a kind of just 2 days requires here, 2 days require here, 2 days here, 2 days here, and then again. So it means weekly, means 8 days, and if 2 days we are stopping our system, then again it is 8 days. So it is irrigation period, 8 days. This is basis for irrigation system capacity and equipment design. Reason being, suppose we have a big farm, in a single day it cannot be covered, right? It cannot be covered in a single day. So we need to design in such a way that pump is running, our water supply is continuous, and it is irrigating this whole farm fields in such a way that here the first field, suppose it is this, at first field it is this one, irrigation frequency is not disturbed, or it is getting water at the same time it is designed. Just like it takes 1 day for each block, so 1 2 3 4 5 6, it should be designed in such a way, either it is system or it's a pipeline, that in 6 days it is covered, and this requirement of water again to the field one is after 6 days, or it is the 7th day when we need to apply water here. So that is called the irrigation period. So irrigation system should be designed such that it is not greater than irrigation frequency. It should not be like just you are covering in 2 days and rest 10 days, it is ideal. So system should be designed in such a way that it is working with its full efficiency. So that is the concept of irrigation period design after irrigation frequency. Now, this is what we have already discussed, but to make it very clear, soil water content like available water, you have already learned it's a matter of difference of water between field capacity and building point here. So it's available water to the crop. So amount of soil moisture held between field capacity and permanent building point or building point. But this is in terms of if we are taking this particular notation here in terms of bed basis moisture content. If it is in percentage, then divided by 100, difference between these two. And to convert this first in volumetric moisture content, it is apparent specific gravity multiplication. And if we are talking about the root zone depth, we need to multiply by the depth of the root zone. So that is available water in this root zone depth in between field capacity and melting point soil moisture content that is measured on bed basis or mass basis. Readily available water, you know this available water, readily available water, that is volume per unit surface area of soil water between field capacity and critical soil moisture content. This is the simple idea that per unit depth. Volume per unit surface areas means per unit depth of root zone basically, and this is readily available water. This is the simple idea here. Let me go back this one. This is your readily available water, means this is easily available to the crop and crop is responding to a maximum extent or full extent. It is giving without any, means yield is having no loss condition in this reduction of water content. So this is basically the threshold condition that is called the readily available water. So it is in the same way here like this, field capacity minus critical moisture content when it should be irrigated. If we know that theta at the time t, that is critical moisture content, we can find out how much is the readily available water in this root zone depth of the soil. So maximum allowable, it is allowable deficit or deficiency, or it is also called sometimes management allowable deficiency, means it is the same. It is field capacity, and here in this graph, if you have seen, this is particular condition, that is time t, that is critical. So this water content is basically management allowable deficit in between here from field capacity to melting point. This is the total available water, or it is called available water from field capacity to melting point. This is readily available water between field capacity and critical soil moisture content, that is at time t, and maximum allowable deficiency. This is the total, and out of this is the allowable deficiency or deficit condition. So this is basically maximum allowable deficiency, that is the ratio of readily available water and available water. Readily available water and available water. So this is always less versus this is high. This is total available water. So if we are taking this as x1 and this total is x, then MAD is simply idea x1 divided by x. So this is for different crops, like vegetables can go up to 0.5. Half of the water can be depleted from the available water, and there will be least loss of yield or return. For other crops, it is 0.65, means this particular portion should be 0.65 and here it should be 0.35, or maximum 30% water should be used. When depletion remain 0.65, we should irrigate. Potato means it can be up to 0.3. So in irrigation scheduling, readily available water, now you can see from here, readily available water, or here if we can see readily available water divided by total available water. So readily available water is management allowable deficit into available water, and available water is written here D into a field capacity minus permanent melting point. So it is like this. So hope you have very clear idea. It is simple idea of a soil root zone depth, maybe in different layers we can take, and we can think about loss of moisture because of ET, and it is change in soil moisture content. So we can take these two ideas to fix when we are knowing that this is the threshold soil moisture content which will affect the yield of a crop. From here you can see that it is depending, this particular will be here, or it will go to here, or somewhere here, or maybe here. Depends on the crop and soil condition. So we can plan when to irrigate and how much to irrigate, because it's a difference between field capacity and management allowable deficit, or it is basically the threshold or critical soil moisture content. Now, once we know that, then we need to think about irrigation scheduling. So what is irrigation scheduling? It's a process of determining when to irrigate, that I started from beginning, and how much water to apply per irrigation. That you have almost learned, but it is now getting structured condition. You are learning as an structured knowledge. What is advantage of irrigation scheduling? It is essential for efficient use of water, energy and other production inputs, like when to prepare the field, when to go for transplanting or planting or sowing, and how much water it should be used to irrigate this time, next time and onward. This also scheduling also improved crop yields as well as quality, water and energy conservation, and lower production cost. It is reducing or reduced production cost rather than lower. It reduces production cost. So irrigation means once we are supplying irrigation scheduling, maintaining a water level in the field. Now you can see it is suppose field capacity. From line diagram you have learned that it is field capacity, then it is reduced to critical moisture content. This is wilting point, this is permanent wilting point, and so on. So it is shown from this, say, bucket system. So it is field capacity, and if it is more than this, it is simply gravitational flow of water. It is lost from the system. It has no use in soil. So from field capacity to wilting point, this is the level in the tank. It is water that can be used by the plant up to the root zone depth. And then there is certain amount of water which is not available. Beyond permanent wilting point, there is as well water which is not available. It's hygroscopic condition of water which is not available water. So this is the system. This is readily available water. This is manageable, managed allowable deficit or MAD level, means up to this it is readily available. Then after, even it is available for the crop, but it's only for survival. So this is the system. It is simply showing this line diagram we have already discussed. And let us find out how to schedule irrigation. So irrigation scheduling, it is basically full irrigation. Suppose we are scheduling a full irrigation. What does that mean? It involves providing the entire irrigation requirement and results in maximum production. Means whenever it is required, whenever the moisture is reaching to the critical condition, we are applying water. So it is basically the full irrigation without any stress to the plant. However, if we are exceeding this level full irrigation, exceeding it means if we are applying more than this water, then it decreases the crop yield by reducing soil aeration and restricting gas exchange between soil and the atmosphere. Means it will be more moisture in the soil than field capacity condition. Full irrigation, it's economically justified when water is readily available and irrigation costs are low. Means we can supply the whatever amount or exactly what amount plants require, we can apply. Conditions are only like this, water is readily available or it is available, and cost of supplying water is not high or it is low. Full irrigation is accomplished by irrigating to minimize the occurrence of plant stress. Means there is no stress or almost zero stress to the plant, and then only it is giving the maximum potential output in terms of yield. So it is here irrigation schedule for full irrigation. If two conditions are there, there is sufficient water and there is not high cost of application. Now it is deficit irrigation. Second term in scheduling is deficit irrigation. Means it is less than the full irrigation, so it is deficit irrigation. It is partially supplying the irrigation requirement by the crop, like it is not 100% requirement, say it may be 90%, maybe 95%, or maybe even less than that. So it is partial supplying condition of irrigation requirement by the crop or plant. This reduces yield a little bit as a small amount of water, energy and other production inputs are used. So a small amount of irrigation, water, energy and other production inputs are used. So simply less amount of water, so it reduces a little bit yield. However, it is economically justified. It is not like that in 100% irrigation, suppose it is production of 3.5 ton. So here in deficit irrigation, we cannot compromise to get yield or production less than even 3.2 ton. But if it is reducing to say 2 ton, then it is huge loss. 1.5 ton per hectare loss we cannot simply take. So it's economically justified. This difference of 0.3 ton, it's okay because the same amount of economy or money we have saved in less supplying water and other input conditions like pumping water, like preparation of the land or whatever it is. So it's economically justified when reducing water application below full irrigation that causes production cost to decrease faster than the revenue decline. So it's basically difference is justified, but not in this case. And deficit irrigation used when water supply or irrigation system limit water availability. Suppose there is less water availability, like in the arid region, Gujarat or maybe Rajasthan. So it's certainly we need to plan a deficit irrigation because there is less availability of water, maybe more area that is under cultivation. So better to have some output from all the area that is economically justified to use the same amount of available water from the source. So that is usual there. And it is accomplished deficit irrigation by allowing plant stress during one or more periods of growing season. That takes are taking care that adequate water is supplied during critical growth stages. So plants are say sowed, it is germinated, it is growing, it is flowering, it is filling up the grain, it is maturing, and then it is harvest. So there are critical growth stages, like if it is not grown fully in terms of its biological growth, then it will not attain a good flowering, and if not good flowering, it is not good grain filling, and then automatically it will be least harvest. So these are a few conditions where their stress should not be, or stress of water is not allowed. So deficit irrigation certainly planned in such a way that these critical growth periods should be avoided, or they should not encounter with this reduced availability of water. Otherwise, it will be more loss of outcome. So it is basically the full irrigation, then deficit irrigation, then another method like irrigation scheduling. We are scheduling now properly. So we can have a kind of bookkeeping to find out the critical moisture content that we have denoted earlier, T at a particular time T, when after this critical period or last condition starts. So we can have a kind of bookkeeping method to find out when to irrigate the field. Like moisture status of soil is calculated at various times using the evapotranspiration value. Just like here, we have started from this particular date 1. Age of the crop is simply 20 days. So every day then after, we are simply accounting the evapotranspiration. Like on first day it was 4 millimeter, second day 6 millimeter, third day 5 millimeter, and so on. And it is accumulated ET basically, which defines when to irrigate. Like for an example, we need to irrigate when there is a loss of 100 millimeter of water as evapotranspiration. Reason being, the moment 100 millimeter of ET is lost from the area, field will reach to critical soil moisture content from maybe somewhere field capacity condition. So crop is irrigated when the estimated soil moisture level attains a predetermined value, that is critical moisture content. So it's basically called the bookkeeping method of irrigation scheduling. Irrigation scheduling, full irrigation schedule, deficit or partial irrigation schedule, bookkeeping method we can take to find out those, and then methods based on soil indicators as well we can use. Like simply we are measuring soil moisture. So soil moisture content is monitored and field is irrigated when predetermined deficit is reached, just like theta critical, that is denoted earlier theta T. So irrigation interval is fixed for each crop depending upon the depletion permissible for that crop. It may be, but for different season it may change. Reason being, the same amount of ET is not every day and for every season. However, irrigation interval is fixed for each crop depending upon the depletion that is permissible for the crop to reach this condition. Permissible depletion vary according to the growth stage. Now it is coming the same what I am telling. Means if it is growth stage or age of the crop, growth stage especially for deficit irrigation schedules. Soil indicator of when to irrigate also provide data for estimating the amount of water to apply per irrigation. When to irrigate, that is simply soil moisture content. So it's a method based on soil indicator when it is reaching to a certain soil moisture content condition there. And this is the simple idea, means comparative kind of understanding if you can make, because I tried to put everything here. How to find out, here it is soil indicator, so simply it is soil moisture, and we have learned different methods of soil moisture measurement. From there we can take inference or help to find out irrigation interval, irrigation frequency, and irrigation scheduling finally. Just like here, we have method that is used to measure the soil moisture, like feel and appearance method. If you recall, we discussed. We can just take the soil, see by taking our hand, and we can use this for irrigation scheduling purpose. So advantage of this, it is very simple, requires nothing, only skill is required to find out the right condition to irrigate. However, its principal disadvantage is time consuming. You need to go and see every time. It is very much approximate, requires interpretative skill or experience, a lot of experience, and then only you can use this method to schedule irrigation. Then you can measure the soil moisture by using gravimetric method. We need a lot of lab facilities, instruments like soil auger, scale, oven, etc. Though principle is simple, accurate, but it's sampling, we need to go for destruction sampling and it requires time. So it's an advantage that sample and results are very accurate, but disadvantage is it's a time consuming and destructive method. We need to take sample from the soil, or it is taking those sample out from the place of soil. So we cannot measure many times at the same point, same location, but we need to take sample from different depths to find out the right information about soil moisture. Third method of measuring soil moisture or potential is tensiometer. Soil metric potential is measured. Tensiometer and gauge are required there. Its advantage is that measures functional parameter affecting slow water flux. Accuracy is very good, right? And it reads soil moisture tension sometime. However, its careful is more important. And the second condition is it cannot get used when soil moisture suction is more than 0.8 or maximum 0.85 atmospheric suction pressure. So these are different methods we can use to schedule, to plan irrigation, frequency, timing, and amount. Other methods which are used to measure the soil moisture like electrical resistance method, neutron scattering or neutron probe, TDR method of measuring soil moisture. Like electrical resistance, it's porous block, it is required. Its advantage like is provide indirect measurement of soil water content, but it is means disadvantage is that it is getting affected because of salinity if they are in the soil. Not sensitive at low tensions, means at field capacity condition it is not very much effective. It's not effective in core textured soil. It's a short life of the block. Neutron probe, it is neutron probe and access tube that is required. Gives very good information about volumetric soil moisture content. Repeatedly we can use for different depths. It is very quick and accurate as well, but now it is not allowed to use this neutron scattering probe. So it's expensive, however, to purchase it requires special handling and storage condition of neutron scattering probe. And it is affected by charges in soil organic matter. So it is not working always good without calibration. We need to calibrate the instrument first. Like TDR, if a TDR probe is required, it is accurate, can be automated by continuously and can take continuously measurements. It is very expensive, monitors relatively small volume of area or soil, requires careful installation, and so on. So it is particularly means careful, we should be in gravelly and heavy soils. So these are the methods which were used to measure the soil moisture, and these can be used for irrigation planning, irrigation scheduling, right? And to find out frequency and amount of irrigation in each time interval. So other methods as well, methods based on the plant factor. Earlier it was time basis, ET. Second, it's soil moisture measurement by means accumulating ET in time. And now there are methods as well which are using simply plant factors or information that is coming from the plants rather than the soil. So plant factors which are used to schedule irrigation, like plant water stress, that is indicated by its leaves color or its leaf strength and so on. So plant water stress indicates the need for irrigation. Growth of certain parts of the plant color, leaf movement, growth are used as indicator for the plant water stress identification. So rate of growth of say stem length in sugarcane, that is one example. Fruit size in apple and oranges are the simple idea of taking plant factors to plan or schedule the irrigation time. What are the disadvantages of using plant factors? Growth measurement may be influenced by other factors than soil as well. What are those? Like fertilizer. If nutrients are less available, growth will be very slow. And if it is sufficient nutrients are available, it will be a faster growth rate condition. So this is just one disadvantage. Now, different methods, just like earlier it was soil moisture. Here we can see other factors as well are used to measure the plant factor based irrigation or to plant factor based irrigation scheduling, like appearance, like fruit or leaf appearance. We simply use our eyes. Principle is very simple. Yield potential is affected before color and other changes are observed. So approximate, this is simple appearance method of irrigation scheduling by seeing the plant. It is very much approximate, and again it requires a lot of skill and experience. Leaf temperature we can measure to find out if it is sufficient water. Leaf temperature will be controlled to atmospheric condition. However, if it is reduced water availability, leaf temperature will rise with respect to atmospheric conditions. So leaf temperature, it's non-contacting thermometers are available. We can use, can be sensed remotely. That is the advantage of this particular leaf temperature measurement. However, disadvantage, it could be like application methods not well developed. It is very rough and crude method. Leaf water potential we can measure, pressure chamber or thermocouple psychrometer we can use, psychrometer. Advantage of this method, leaf water potential measurement, it indicates irrigated effect of aerial and soil environment on degree of plant hydration. That is correlated with the metabolic processes of the plant. However, it has disadvantage. It's subjected to large diurnal fluctuations, time consuming, requiring sampling skills and so on. And third is stomatal resistance, because stomata are responsible for removing water from the plant. So it basically most important condition for transpiration. It can be measured, stomatal resistance, how much resistance it is developed, but it's very expensive, means condition, time taking, requires high level of precision and so on. But however, we can use these methods, and these are important when we are using something like a remote sensing applications. So bigger area can be connected or can be identified, can be estimated in a very short period of time. That's why methods should be in mind, so that if we can realize, we can use at later stage to find out more effective and more widely in terms of space used techniques to schedule the irrigation or irrigation scheduling. We can as well use application of water balance method, like water balance models consist of determining the different components of inflow and outflow from the given field for a chosen period of time. If you recall, we have learned earlier as well, ET estimation. We know that it's rainfall, it's irrigation, losses are deep percolation, lateral flow, surface runoff, and then we can go for balancing. So inflow could be like rainfall and irrigation, outflow, ET, drainage, seepage, percolation. It is separately applied for lowland paddy as well as irrigated crops. So here for these two, lowland and upland paddy, water balance equation for lowland paddy we can write like this. So that is water is stored in the field at the end of the day. It's basically water stored in the field at the start of the day, means it's a daytime length. So at the end here we are simply trying to find out from the start initial is effective rainfall for the day. You know effective rainfall now. And IR is the depth of irrigation for one day. ETC is the daily actual crop evapotranspiration. S&P is basically the mean daily seepage and percolation loss of water from this field, and it's a drainage DR for the day. So in that way we can balance the water for the day to find out water requirement in lowland paddy where it is flooded situation there. The water is flooded here. We need to find out how much water it is lost on every day and what is currently available at this time. This defines whether we need to irrigate or when we need to supply water so that it is desired amount of flooding is maintained there. What about upland? Upland irrigated crops. So this is the amount of soil moisture on the day. This is the previous day condition. This is the rainfall on the day, daily effective rainfall. E is effective evaporation of the day. It's basically actual transpiration. So evaporation, transpiration. This is depth of irrigation water we have applied. So it is plus. So these are removing condition. These are addition condition. So all adding water in the area or in the field, it is added, and all possible removal of water just like evaporation, evapotranspiration, or evaporation, transpiration and deep percolation are removed. So that gives the water balance equation to accumulate. Again, every time we are simply trying to find the critical soil moisture content. What is at current? The moment it is matching with this, we are simply irrigating the field. So this can be used because this is for I written for a particular layer. It can be used, or this kind of equation can be used for entire root zone depth for each layer of the root zone. Either it is layered system we are assuming, or it is single layer even we can calculate. It depends on our requirement of accuracy. So this is the basic idea about irrigation scheduling. Once we have learned, and then next we will discuss about irrigation efficiency and methods of irrigation. Only two aspects are remain. Methods of irrigation, that is our last. And this is irrigation efficiency. We are having different condition. Crop now you have learned, scheduling, planning, conveyance we have learned, measurement of water we have learned. So we need to find out what is the efficiency, irrigation efficiencies, and then irrigation methods to complete this particular aspect. So if you have any query, you can ask, otherwise it's your maybe next class. So you are free to move. Any query? Anybody, please? And nobody is there. It was only recording that was attending lecture.
Sir, no queries.
No query. Okay. So Monday we will be having a test. I have uploaded all the files or all the lectures before this. So I will ask not from this particular topic or idea, but previous all topics. Monday 10 to 11 will be a test. And Monday 2:30 or yes 2:30 to 5 o'clock there will be Viva, lab Viva. So I will talk to Professor Soni, half of the student on Monday to me and remain half to Professor Soni, and then Friday we will exchange again. So this will be hopefully scheduled. Do you have any query?
Sir.
Monday test, Monday Viva, Friday lab Viva, and that will be, I hope, sufficient for mid learning. So no query, then you can go to your next class. Thank you very much. We will meet on Monday again for the test, but prepare well for your test. Okay. See
Thank
you.
you, sir.
Welcome.